Welcome everyone to today's lecture. And there are only 35 students online, so I don't know if that's because we're close to the end of the term or if something else is happening today. Anyway, let's start. So last time we talked about the serializability of schedules, and so we discussed this schedule here and we drew its serialization graph. And now we're going to look at this slightly different schedule, again, for these same three transactions, T1, T2, and T3. Okay, so let's draw the serialization graph for the schedule F here. So again, we have three nodes, T1, T2, and T3. And now let's see what kind of edges we have. So let's start at T1. So T1 here, we have a read item of X and a write item of X. Okay, and do we have any conflicting operations here? Any edges that I should add? Any suggestions? Right, so I need to add an edge from T1 to T2. And I will label it with what? Yeah, definitely X. Anything else that I need to label this edge with? Also Y, right? Because down here I have this write operation. So I'm writing item Y. And also here I'm writing item Y. So these two writes will conflict. So we'll also need to add a Y here. Okay. And let's look at T1 and T3. Is there any conflict there? So T3 doesn't access X, so this is fine. And you can see there are no operations after these two in T3, so there's no edge from T1 to T3. So let's move on to T2. So I'm reading item Z here. So item Z is not accessed by any other transaction later on, so that's fine. And of course, none of these here are causing any problems. Okay. So T2 does not have any outgoing edges at all. And finally, let's look at transaction T3. So T3 is reading Y and Z here, and we can already see that this will conflict with this write of item Y, and also here with this write of item I. So there's an edge from T3 to T1 and to T2. Both of them we have Y labeled here, and we're also writing Z here, and there's a read of Z afterwards in transaction T2, so we also need to add a Z here. So is that a question? Anyway, yeah, so there's no cycle here. Okay, so you can see if you look at the directed graph, there's no cycle here. And so what are the two equivalent serial schedules? Or let's first check how many equivalent serial schedules there are. Well, how do we do that? Well, we start with the node that doesn't have any incoming edges. There's at least one because there's no cycle. In this case, this is T3. So I will first execute. So the serial schedule that I'm looking at will first execute all the operations of T3. So then I will just remove T3 from my graph and check what's left. So now I only have T1 and T2 left. So now T1 is the vertex that does not have any incoming edges. And therefore, my serial schedule will look like this. Okay, so this is the equivalent serial schedule that is equivalent to this concurrent schedule F here. All right, so I hope this is reasonably clear. We also had a chance in the tutorial to look at this. So now let's talk about the recoverability of schedules. So whenever a transaction is submitted to a database management system for execution, the DBMS is responsible for making sure that all the operations in the transactions are completed successfully, and their effect is therefore recorded permanently in the database. Of course, if that's not the case, if the transaction does not complete successfully, then that transaction shouldn't have any effect at all on the database or any other transactions. Okay, and in fact, when a transaction does not complete successfully, then we say that the transaction is aborted. And in that case, we need to make sure that all its effects are undone. So that's what I mean by a rollback, right? So it can happen that you need to terminate the transaction that has already executed some rights, for instance. And in that case, you're rolling back the transaction. Okay, so you need to undo the already processed operations of such an aborted transaction. So why do we need to do a rollback in the first place? Well, there are several reasons for it. Sometimes we need to do that to break a deadlock, and also to maintain consistency. So we'll encounter several instances where that is necessary. All right, so what we want is essentially we want to have schedules, concurrent schedules of our transactions that are recoverable. Okay, so we can roll back transactions without causing any violations of the database consistency. And also we want to maintain the all or nothing property. And I hope you remember what the all or nothing property is. That basically means that either the transaction is completely executed or none of its operations take any effect. Okay, so this brings us to the definition of a recoverable schedule. So here's the formal definition. So we say that a schedule S is recoverable if for any two transactions, Ti and Tj, if you have if it's the case that Ti reads an item that was already written in transaction Tj, then it must hold that Tj commits before Ti commits. Okay, so this is a bit formal, but basically the intuition behind this definition is that we want to ensure that a committed transaction never needs to be rolled back. Okay, so for instance, if I in this transaction Ti, I'm reading some item that was previously written by some transaction Tj. So now let's say I don't have this property here that Tj needs to commit first. So let's say Ti commits first. Okay, so Ti has read this item and then commits. It does something, it writes maybe another item after that depended on the result that it read, and then it commits itself, and its effect become permanent in the database. And then later on, Tj aborts. Okay, so then we have a problem, right? Because now what happens is that this write that Tj did is undone because Tj aborted, but we already committed Ti that read that value. Okay, so now we have a problem because we need to kind of undo what Ti read, even though it has already been committed. Okay, so this is just an intuition behind this definition here. Now, it can happen that if you roll back one transaction, you might need to roll back other transactions too. Okay, so in particular, if one transaction aborts, this might cause a series of rollbacks. And you can think of this series of rollbacks that we have as kind of like a cascade. So that's why this is called a cascaded rollback. And in fact, any uncommitted transaction that has read a data item from an aborted transaction must be rolled back to ensure consistency. So now that we have this definition here of recoverable schedules, let's see how we can actually ensure it. So there are several things we need to keep in mind here. So we need to make sure that we don't have any dirty reads, right? So that's one way how to ensure recoverability. So you don't want to read uncommitted data items. Also, we wouldn't want to have premature writes. So that means you don't want to update. So if another transaction has updated an item and that transaction has not yet committed, then you also shouldn't be allowed to update the same item. Okay, so that's what a premature write is. So you also want to avoid these. And in fact, we can formulate several recoverability conditions. So the first one is what is known as a strict schedule. So a schedule is strict if we delay the reading or updating of an item X until the last transaction that updated X has been committed or has aborted. Okay, so if this condition holds, then the schedule is guaranteed to be recoverable. And this is in fact the strongest condition that is used. Now there is another condition, which is the cascadeless definition. So we say, so basically, if a schedule is cascadeless, so this is, so the name comes from, this cascaded rollback that I just mentioned on the previous slide. That would be become clearer later on when we look at an example. So when is a schedule cascadeless? So if every transaction reads only items that were written by committed transactions. Okay, and this, if you have this property, then you can ensure that there's no cascaded rollback. Now, in terms of strength, the strongest condition is that a schedule is strict, because a strict schedule implies that it is also a cascadeless schedule. All right. And in fact, since these are both recoverability conditions, if a schedule is either strict or cascadeless, then it's also recoverable. All right, I know there are a lot of definitions flying around here. So let's look at some examples. So let's look at this first example here, where we have two transactions, T1 and T2. And you can see we have some reads and writes. And here we have some, so this could either be a commit or an abort, and similarly here. Okay, so of course, in an actual schedule, it's either a commit or an abort. So you can't have both like I've written here. I just want to give us the option to study the schedule in either case. And in fact, let me start a poll and see if we understand whether this is recoverable. And keep in mind that strict is the strongest condition, cascadeless the second strongest, recoverable the third strongest. Okay. And of course, if it's not non-recoverable, then it's neither of the other three, because that means your schedule is, neither strict nor cascadeless nor recoverable. and try to finish in the next 20 seconds. All right. Let's close the poll. Okay, so the majority of you think that the schedule on the left is recoverable. So this one here. All right, so let's see what can happen here. So what happens if, let's say, transaction T2 commits and transaction T1 aborts? Is that a problem? So let's say this is our actual schedule. And in fact, you could think of this right here. Let's say this right corresponds to, like, you know, adding 500 to some account. And then here I'm reading this account. Let's say it's called A. So I'm reading 500. And maybe I'm doing some other operations here before I'm committing based on this value of 500 that I read. And unfortunately, later on, this transaction T1 is going to abort. So this 500 up here is, you know, was never added to the database. But unfortunately, this transaction T2 was already committed. And whatever it committed was based on this value that it read here, this 500. Okay, so we can already see that if the schedule is in this form, that T2 commits, but T1 later on aborts, then we have a problem. And in fact, this schedule here is non-recoverable. Okay, so why is it non-recoverable? Well, if you recall the definition, a schedule needs to be recoverable. If you look at these transactions T1 and T2, so whenever, you know, T2 reads an item that was written by the other transaction, then we need to make sure that the other transaction commits before this transaction here. Okay, so we would need to reverse the order of these two commits here, or commit aborts here, then we're fine. All right, and in fact, this brings us to the second schedule here, right? So you can now see that we swapped the order of these two lines. So now this makes it recoverable. Okay, so now we learned that this is recoverable because this commit here happens after this commit. And just to give us some understanding why this is better, why this is preferable compared to this schedule here. So again, let's assume that, you know, this transaction here aborts and this transaction here commits. So exactly the same thing happens as over here. All right, and so in that case, what will happen is that, again, so I'm adding 500 here to my account, right? And then in this transaction, we're reading this 500, and later on, this transaction here aborts. Okay, so this invalidates this right here. So this is going to be undone. And then actually, I won't be able to commit this transaction. Okay, so in fact, this transaction won't commit in that case because it has read a value that was written by an operation that has been undone. And therefore, I wouldn't commit this transaction. Okay, so I would abort it. All right, and now I don't have a problem because I don't need to do anything else. I can just abort this transaction after I abort this transaction and nothing else has happened. Okay, so I don't need to like undo transactions that have already committed, which I would need to do in this schedule over here. And that's the reason why this is a recoverable schedule and this one is not. Okay. Now, what would we need to do? So in fact, recoverable is the strongest condition that this schedule here satisfies. So what would we need to do to make this a strict schedule? So there's a question, how do we fix A or B? What do you mean by fixing A or B? So A and B are just some data items that we're reading and writing here, right? Oh, so I'm asking about this schedule here. So we determined that it's recoverable, but actually what I asked in the poll is, I've asked what is the strongest recoverability condition, right? So if it's recoverable, then that's great. So that's, of course, the weakest recoverability condition, but there are two stronger ones, right? Cascadeless and strict. So I'm asking, how can we make this schedule here satisfy the strict definition? Okay, and just to show you what strict means, right? So we must delay reading or updating of an item X until the last transaction that updated X has committed or was aborted. So how do we fix this schedule here on the right so that it is a strict schedule? So basically we would need to delay this read here until after this commit or abort here. Okay. Because then we satisfy this definition here. All right. So we would need to kind of push down this read here. Then it becomes a strict schedule. So the difference is that, for strict schedule, I'm delaying reading or writing, okay? Whereas if you look at the definition of cascadeless, it says that every transaction reads only items that were written by transactions that have already committed, okay? That's a good question. In fact, we're going to look at cascadeless schedules now. And let me start another poll for that. So here we have another schedule now with 3 transactions. All right, and again, I'm asking if this schedule is recoverable, and also there are some sub-questions involved here. again, this could either be a commit on abort, and similarly here. So just keep in mind that in an actual schedule, you either have a commit or an abort, so you can't just write commit/abort, because then it's not really a schedule. It's just one of two possible schedules. Okay, and try to finish in the next 20 seconds. All right. Okay, and most of you think that T2 and T3 need to be rolled back if T1 aborts, and that is true, in fact. Okay, so this is a recoverable schedule, and you can see an example here of cascading rollback, right? So now you can see also why this is called cascading rollback, because it looks like a cascade. So if we have an abort here in T1, then also T2 and T3 need to be rolled back, okay? All right, and the reason for that is, of course, because T1 wrote this item A here, and it was read here in T2 as well as in T3. So they can't commit after reading that item. Also, by rollback, let me go back to that. So, we want to undo the processed operations of an aborted transaction when we do a rollback. Okay, so you're kind of rolling back everything that transaction has done. All right, so we will practice these recoverability conditions more in the tutorial. And now I'm gonna move on to a different topic, or rather the next topic. So we'll open the second slide set. Which will be about concurrency. Okay. All right, so now we're going to talk about concurrency control. And we're going to start with something known as two-phase locking, abbreviated as 2PL. Okay, so there's another question in the chat. So is there a condition that is cascadeless? So yeah, so strict is the strongest condition, meaning every schedule that is strict is also cascadeless, but not the other way around. Okay, so you could come up with schedules that are cascadeless but not strict. All right, so let's continue with concurrency control. So what's the purpose of concurrency control? Well, of course, we want to preserve the database consistency, and that becomes more complicated if the transactions that are concurrently accessing a database. And we already seen that all our schedules should be serializable. So that's something we discussed last week. And basically, this means that all schedules are correct. So we can just say /correct when we say serializable. The reason why we say that, why we're saying that they are correct is that you know, serializable means that a schedule is equivalent to some serial schedule, and only serial schedules really are correct, right? Only if transactions happen one after the other, that is like a well-defined behavior. Another thing is why we want to have concurrency control. Well, we want to maximize the system performance, because of course we could simply serialize all schedules in the sense that I'm just, you know, I'm not letting any operations happen concurrently. I just always force all schedules to be serial, but that won't give us a good system performance. So another goal is to achieve a higher level of concurrency. Now, what's the purpose of concurrency control? Well, if we have a concurrent execution environment, and if you have two transactions, T1 and T2, and maybe T1 conflicts with T2 over some data item X, then the concurrency control mechanism will decide whether T1 or T2 gets to access item X, and whether the other transaction is either rolled back or needs to wait until it gets its turn. So one commonly used approach to synchronize the access of database items by concurrent transactions is to use so-called locks. And basically, a lock is a variable that is associated with a data item that you know, tells us the status of the item with respect to the possible operations that you can perform on it. So for instance, an item could be locked for writing, meaning you can't access the item for writing at this point in time. Now we will see that the main techniques that are used by you know, to control concurrent execution of transactions. So those are based on the concept of locking data items. Okay, so locking is an operation which secures either the permission to read a data item for a transaction, or the permission to write, meaning update a data item for a transaction. So an example could be this: if we have some transaction Ti, and we perform this operation write lock X, then the item X is now write locked by the transaction Ti. Okay, that's the semantics of this operation write lock. And the implication of this is that item X cannot be accessed by any distinct transaction Tj. On the other hand, maybe I only want to have a read lock on X, so then I will execute read lock. In that case, item X is now read locked by transaction Ti, and X can be read but not written by any distinct transaction Tj. So depending on what I want in my schedule, I will call either of the two. Now, as the user, as the end user of the DBMS, you're not going to actually write these operations like write lock and read lock. So that will be done by the concurrency control subsystem. Okay, so in SQL, for instance, there are no functions that you can call that are called write lock or read lock. And in fact, you don't need to worry about them because it's all already done for you. Now, since we can lock an item, we should also be able to unlock it. And of course, unlocking is just the operation that removes these permissions that I acquired up here from the given data item. Okay, so if I execute unlock X, then the data item X is made available to all other transactions. Now, just a note, these write lock and read lock. So those locking operations, they are performed before any write or read operation. Okay, unless you have already acquired it in an earlier operation. So that really depends on your schedule. And for the purpose of our discussion now, we're going to consider this read lock and write lock and also unlock to be atomic operations. Okay, so we just assume that they happen in an instance. Now, there are several modes that you can lock a data item. So we are going to consider the shared locks, which are the read locks, and the exclusive locks, which are the write locks. So I already mentioned to you the read lock. So so basically multiple transactions can hold a shared lock on X for reading. So if you have two transactions, let's say T1 and T2, then both of them can execute read lock of X, and neither of them will be blocked. Okay, but no write lock can be applied on X during that time, because a write lock is an exclusive lock. Okay, so if we execute write lock of X, then we're in exclusive mode, and no other transaction can hold a lock on X at the same time. So in fact, if some other transaction has already or is already holding a write lock or a read lock on X, then I will be blocked when I execute write lock. So down here we have this conflict matrix, which summarizes this discussion. And these entries here in the matrix, those tell us whether the simultaneous access is allowed. Okay, so multiple transactions can hold a read lock, right? But as soon as one of them has a write lock, then no one else can hold any other lock on that item. Now, in some cases, I need to upgrade a lock. For instance, I might have first acquired why the PDF is different. The PDF of what? Oh, I think so. Actually, these two slides are in the PDF. That they're just they're coming later. I just before the lecture I decided to move them earlier. Okay, so they're both there, but they're further at the back. I'll update them after the lecture. Don't worry. Okay, so sometimes we need to upgrade a lock. So let's say if transaction has a read lock on X, okay, and no transaction TJ has a read lock on X, then you can convert the read lock to a write lock. Okay, so then you convert your shared lock on X to an exclusive lock. All right, so that's how you can upgrade a lock. Otherwise, you know, if there are some transactions TJ that have a read lock, that have also a read lock on X, then TI will need to wait until all the other read locks on X are released. On the other hand, sometimes you may want to downgrade a lock. So for instance, you might, a transaction TI might currently hold a write lock on X. And that implies, of course, that no other transaction can hold any lock on X. And then I can, you know, downgrade the lock by converting a write lock to a read lock. All right, so these are the basic operations that I can perform on these locks. And now let's see how we can actually use these locks to do something useful. So let's discuss some concrete locking mechanisms that ensure serializability of concurrent schedules. So let's talk about basic two-phase locking. So we assume that each data item has a lock associated with it. Okay, so you can think of it as having a lock entry in some lock table. I'll talk more about how we can implement such a lock table later on. So basically what happens is that when you have a schedule of some operations, some reads and writes, then your scheduler will automatically create corresponding lock operations for each of the operations in your schedule. Okay, so if we have an operation OI that accesses some data item X, where I refers to the transaction, then the scheduler will just create a lock operation OLI of X. Okay, and it will need to execute that before it can actually execute OI of X. And two-phase locking follows these two rules here. So the first one is that when the scheduler receives some operation PI of X, it will test if the lock operation PLI of X conflicts with some other lock operation that has already been set. Okay, some let's say QL set by some transaction J of X. And if there is a conflict, then we're just going to delay this operation PI of X. And thereby we're forcing the transaction TI to wait until it can actually set the lock that it needs. Otherwise, we're going to create this lock operation, PLI of X, and we're going to send the actual operation that we want to perform, which was PI of X, to the data manager. The second rule is that once the scheduler has released the lock for a transaction, it may not subsequently obtain any more locks for that transaction on any data item. Okay, so you can first start locking the items that you want and start using them. But as soon as you start releasing a single lock, you can no longer acquire any new locks in that same transaction. What other transactions do, of course, is a different story. Okay, so visually we can describe this this two-phase locking by a growing phase and a shrinking phase. So down here in this diagram, you can think of the time flowing from left to right. And on the y-axis here, we have the number of acquired locks. Okay, so initially we don't have any locks, and then we're acquiring a lock. So this is denoted by moving one up in the y-axis. So now we hold one lock. Okay, and then time goes on. I'm doing some more operations here. I'm acquiring another lock, and so on. I'm acquiring the third lock, fourth, and the fifth. And I'm here I'm doing many operations in between, right? So we don't care about these operations. We're only looking at the locks that we're acquiring in this diagram. And at this point, all the items that I'm accessing have already been locked, and I might have already performed some other operations. And now I'm unlocking the first lock. Okay, so this so now the number of locks that I'm holding in this transaction is reduced by 1. And from that point on, I can only start releasing all the other locks. So I can never go back up. Okay, so there can't be any. So that's why there's like this growing phase, which is this part here, and the shrinking phase. All right. And the nice thing about having such a, or rather this basic two-phase locking rules here is that it guarantees you that the schedule is serializable. Okay. So if all the transactions follow this schematic here, that they only acquire locks up to the point where they release the first lock, and they no longer, then they don't acquire any new locks. If all the transactions adhere to this, then you can be sure that the schedule is automatically serializable. The reason for that is that in your serialization graph, you can never have a cycle between two transactions that conflict. So there's a question, so what do you mean by that? So do you mean you can acquire any lock in this phase here? So this is the shrinking phase, right? So in the shrinking phase, I can't acquire any locks, right? So the arrow, we have only down pointing arrows here. The reason for that is that this rule is this rule here, okay? So once we have released any lock for the transaction, you cannot obtain any more locks for that transaction, no matter on what data item. Okay. So once we start releasing locks, we need to release all the other locks one after the other. All right, so let's look at some concrete examples here. And here we have two transactions, T1 dash and T2 dash. Okay. So again, let's run a poll. Right, then try to finish in the next 20 seconds. Okay. All right, we have an even split here for these two transactions, T1 and T2. And most of you think that T1 dash and T2 dash adhere to two-phase locking. So let's take a look. So let's see if there are any problems. Okay, so let's see what happens here. So we're acquiring a read lock for Y, then a write lock on X, then we're unlocking Y, and now we need to check if there are any other locks are being acquired later on, and in fact they're not for T1 dash. And similarly for T2 dash, we're acquiring a lock on X, one on Y, then we're unlocking X, and we're unlocking Y. Okay, so the answer here is yes for these two. Now for T1 and T2 here on the other hand, well, we're acquiring a lock on Y, then later on we're unlocking Y, and then we're acquiring a write lock on X. Okay, and I can't do that because, you know, once I start unlocking, I can only keep unlocking. So this does not satisfy the two-phase locking rule. So again, looking at the diagram that we had on the previous slide, so if you drew that for this transaction here, you would be going up, and then you're going down, and then later on you're going up again. Okay, so now there are multiple growing and shrinking phases, and that's not allowed. So unlock releases the, allows other transactions to access a data item. So for instance, if one transaction holds a write lock on data item X, then until that transaction releases the write lock, no other transaction can read or write from that item X. Okay, so at some point, hopefully that transaction will execute unlock X, and then all the other transactions will be able to access it. All right, and let's continue here in 10 minutes after the break. Meanwhile, I will try to update the PDF of the slides. So you have the updated version. All right, so let's continue. And I see there's a question in the chat. So T2 dash needs to wait for T1 dash to unlock X. Let's see. So the thing is, I didn't really specify a concrete schedule here, right? So I'm just specifying the operations that these two transactions are performing. Right, so it really happens what the actual schedule is. Okay, but in general, if if T1 acquires a write lock on X, the node transaction will be able to perform any operation on X until this write lock has been released. I guess that answers your question. All right, so let's continue. So there are some potential problems that can occur here. So the first one is deadlock. You might have heard of deadlock before. So a deadlock can occur when you have a set of some transactions, and each transaction in that set is waiting for some item that is locked by some other transaction in the set. So in that case, each transaction is in a waiting queue, waiting for one of the other transactions to release the lock on an item that it's waiting on. But the problem is that the other transaction is also waiting for some other transaction to unlock an item. Therefore, neither of them is going to release the lock. So you have, if you draw a graph of these transactions, this is called the wait for graph. We will see that later on. Then you'll see that you have a cycle in that graph. So that's why this is called a cyclic wait. Okay, so if there's a deadlock, then each transaction is stuck in the so-called waiting queue forever. The second problem that can occur is starvation. So starvation happens when a particular transaction is restarted over and over again. Okay, so it's the transaction is being rolled back many times. That can happen sometimes when you run into a deadlock and you're trying to break up the deadlock by restarting one transaction. So it can happen that you always restart the same transaction, and basically that transaction is set to starve. Okay, so that's why this is called starvation, because that transaction never gets to be committed. All right, so we already learned about two-phase locking, the basic two-phase locking. Now we're going to look at some variations of that. So the first one is conservative two-phase locking. So here the difference, or rather the additional constraint in addition to the basic two-phase locking, is that a transaction must obtain all its lock before it begins its execution. So basically, a transaction needs to pre-declare its read set and its write set of the data items. Right. So a transaction needs to know in advance which items it accesses, and then the scheduler will try to set all the locks to access these items by that transaction in kind of one big step. Okay. And later on, when that transaction is done, it can, or rather, as the transaction keeps computing, you can start releasing these locks. All right. So if all the locks are weighable, right? So if none of the items that the transaction wants to access are locked, then the operations will be submitted to the data manager for actual processing. And when I say operations, what I mean is the operations of that transaction. Okay, so if any of the locks requested in TI conflict with the locks held by other transactions, then none of the locks requested by TI are locked. Okay, so conservative two-phase locking is not like a gradual thing. So you don't like try to acquire these locks one after the other. So you acquire them all in one shot. And so if that's not possible, if some items are already locked, then the scheduler will just insert the transaction TI along with its lock requests into a so-called waiting queue. And every time the scheduler releases the locks of a completed transaction, we will examine the waiting queue to see if all the lock requests of a transaction that is in the waiting queue can be granted. So now the question is whether deadlock is possible. Okay, so let's see again if that's true. So let me start another poll for that, because I'm interested what you think about that. Okay, so since this is a very simple question, let's try to finish in 10 seconds. All right. So most of you think it is possible to have a deadlock. And actually, the answer is no, it's not possible to get a deadlock. Okay, because if a transaction TI is waiting for a lock held by TJ, we know that TI is not holding any locks yet. It's just in a waiting queue. Okay. Now, TJ can't be in the waiting queue itself because it is already holding the lock. Okay, so this waiting queue that we are maintaining up here, that contains only transactions that haven't started yet, so they don't hold any locks at all. Because if you, the way we defined this conservative two-phase locking is that all the locks are requested initially. All right. So there's no hold and wait situation where each transaction has some of the locks that it wants and it still wants some more. And since there's no such possibility, it's not possible to get a deadlock here. All right, so let's look at a concrete example. So let's assume this is our schedules. We have transaction T1 and transaction T2. So we have some writes here, and then these transactions commit at some point. So now what is the scheduler going to do with these operations? Well, it needs to insert the corresponding lock operations. That's what we mentioned earlier on. And since we're doing, we're doing conservative two-phase locking, we can just acquire all the locks at the start. Okay, so T2 will need to acquire locks not just for A, but also for B, because later on it writes B. Okay, so it needs to acquire write locks for A and B. And that's possible because no other transaction holds any locks on these two items. And later on here, when T1 tries to do the same, so we want to acquire write locks for A and B, because this is the point where T1 starts its first operation. And since it also accesses A and B, we need to acquire both locks initially. And it can't acquire these locks. They're being held by T2. So T1 will be blocked. So T1 is not yet executing. It's just in the waiting queue. Meanwhile, T2 can continue. It will write B, then commit, and release its locks. And then finally, T1 can get access to the locks. Okay. Another policy is called strict two-phase locking. And this is the one that is quite commonly used in practice. So if you think back to basic two-phase locking, B to PL, so that basically only determines the earliest time when a schedule may release the lock for a transaction. And for strict two-phase locking, the scheduler can only release all locks after the commit or abort step. Okay. Now, in contrast to conservative two-phase locking, In strict two-phase locking, you don't need to acquire all the locks in advance. All right, so what this means is that a transaction TI's locks are only released after the data manager acknowledges the processing of the commit event CI or the abort event. Strict two-phase locking may result in a deadlock, so it's not as strong as conservative two-phase locking, but it still gives us recoverable schedules, where recoverability is defined as I mentioned before the break. Okay, and the reason why we get recoverability is that it gives us strict schedules, and therefore that's why it's called strict two-phase locking. So a transaction can neither read nor write an item until the last transaction at road X has committed or aborted. The reason for that is because of this rule up here, that we only release locks after we commit or abort. Okay, so it's not possible for another transaction to read an item that has been read or written. Okay, so just for your reference down here, this is just the definition for recoverability. Again, let's look at an example. So we have two transactions, T1 and T2. And let's assume this is our schedule. And now we're going to, now the schedule is going to insert these lock operations. So you can see now before this write A, we need to acquire write lock. So we insert this write lock A operation, and then T1 tries to execute also this write operation. So we need to acquire the write lock for A. And now T1 will be blocked because T2 is already holding a write lock. Meanwhile, T2 will execute. It will acquire now a write lock on B, and then write B. Then it will commit, and only then it can release the lock for A and B. And similarly, T1 will then be able to acquire the write lock for A, and then the write lock for B, finally commit, and then release its locks. Any questions so far? So actually, a deadlock can even occur when all transactions always unlock the items after their use. Okay, so of course you might get a deadlock if you have some transactions that are not so, or rather some database management system that doesn't work correctly. But the point is, if you look at if you look at these locking and unlocking operations, so these are inserted by the scheduler. So the database user or the database programmer only writes SQL, and therefore only does these writes and reads. Okay, but these locking operations and unlocking operations, those are only inserted by the scheduler. So the scheduler will not forget to do that unless the scheduler itself is faulty. In that case, our database management system has a bug. You mean here? So, well, we're looking at strict two-phase locking, so there's no reason for us to lock B here, right? Because the only reason why we're locking A is that we're writing A. Okay, so there's no point for the scheduler to also lock B. But okay, so we're just saying, just let's assume that we also want to write B here. Okay, so, but in that case, we would need to have like, we need to have like an extra operation in here. So here would be another operation that would be write B. Okay, otherwise the scheduler would never insert the write lock B operation here. All right, so basically here in between this write A and write B, we would have like a write B. I'm assuming that's the example you're looking at.
Their question. I have a question.
Yeah, 1 second, let me just, well, it doesn't really matter whether the write B happens here or here, right? So, okay, so let's just see what happens in that case, right? So, so you're saying that the write B happens up here. Okay, so what will happen? Well, since the write B will happen, so the scheduler is now going to try to acquire a lock on B, and in fact it will succeed. Okay, and okay, so I'm not sure I'm following this question. Yeah, so I mean, okay, so then this wouldn't be blocked, right? If we have the write B up here. So we just acquire the write lock, and then we can actually, so yeah, so you're absolutely right that in that case T2 can't do anything, and that's in fact the reason why you can still get a deadlock, right? So I'm not saying that strict two-phase locking can't yield a deadlock. So it may result in a deadlock. Okay. All right, so since someone else asked me if I can give an example for deadlocks, well, here you go. All right, and I think there was another question by audio. Or has that question been resolved meanwhile? I guess so. All right, so again, let's look at how to visualize this strict two-phase locking here. So basically, what happens is that you only have a growing phase. So you don't really have a shrinking phase, because the shrinking phase only happens at the very end, at this point here, when you either commit or abort. Only after that, all the locks are being released. Okay, so we only, so this whole thing here, that is only a growing phase. So this is a more restrictive concurrency mechanism compared to the basic two-phase locking. All right. And let me also draw this for the conservative two-phase locking. So what's going to happen here? Well, if you think back to how this works, is that we require all the locks at the beginnings. Okay, so we have this big arrow going up here because we acquire all the locks. And then what's going to happen? Well, I only have like a shrinking phase over time. And of course, this should be straight lines, but my drawing on the tablet isn't that great. So the difference is that a conservative two-phase locking has only a shrinking phase until it ends. So it doesn't have a growing phase. All right. So what's the performance that we get here? Well, for strict phase, so if we look at strict two-phase locking and compare it to the basic two-phase locking, then the lock holding time may be longer, right? The concurrency may be lower. But on the other hand, compared to conservative two-phase locking, the lock holding time can be shorter because I don't need to acquire all the locks initially. And therefore you might have more concurrency, okay? So in a sense, so I'm seeing this comment here in the chat that conservative two-phase locking is more secure. So I guess in a sense that it doesn't give us deadlocks, you're absolutely right. So if you want to avoid deadlocks at all costs, then you probably want to use conservative two-phase locking, but that's not always the right strategy to go, because if you have transactions that don't interfere with each other often, so there won't be many deadlocks, then you're better off with strict two-phase locking, right? So in fact, strict two-phase locking is better than conservative two-phase locking when the transaction workload is light. So if your transactions are short and they don't really, read too many conflicting data items. The reason for that is exactly that the lock holding time is shorter in strict two-phase locking. Okay. And even if there's a deadlock, we will see some mechanisms later on how I can, either prevent or actually, come back from a deadlock. So I can, for instance, force one of the transactions that cause a deadlock to be restarted and therefore break up the deadlock. And that's sometimes a better strategy when deadlocks happen only rarely. Of course, if the transaction workload is heavy, then you want to probably use conservative two-phase locking, because it's because in that case you have long transactions that access many data items, and deadlock is going to occur frequently, and then the overhead of getting rid of the deadlock will be too much. Okay, and in that case, you just go the safe route by using conservative two-phase locking. So there's a question. Seems like 3 secure systems will be selected based on different situations. So I'm not sure what you mean by that. So no, you don't need to release all the locks in an atomic step for conservative two-phase locking. All right, so let's look at the implementation. So how can we implement these locking mechanisms? Well, you need a lock manager, which will manage the locks on the data items. And I already mentioned to you that we have this lock table. Okay, so what's a lock table? Well, it's just an array that contains a lock entry for each data item. And each entry of the array stores the identity of the transaction that currently holds a lock on the data item. So for most items, that will just be null. And also, apart from the transaction ID, this will also need to include the mode, meaning whether it is a write lock or a read lock. So one thing that we need to keep in mind here is the lock granularity. So if you really want to go on the safe route and you don't care about performance at all, then you could just have a lock for your entire database, right? So if you don't mind that only a single transaction can access your entire database at any given point in time, then you're better off this way. On the other hand, you might even have very fine-grained locks. For instance, you could have locks per each record or per each field of your record even. And depending on which of these options that we choose, we either have coarse locking or we have a fine-grained locking. So if you have a coarser granularity of your locking mechanisms, then that gives you a much higher probability of conflicts, right? Because if I'm locking the entire database, then any two transactions that access the same database will conflict. But of course, the overhead in maintaining these locks will become much lower. So again, there's some trade-off involved. So how is the locking operation actually implemented? Well, I'm giving you this pseudocode here, which is from the textbook. And the reason why I'm mentioning that it's from the textbook is that it has this very ugly go-to statement in here. And I would never write code that contains a go-to statement, even if it's pseudocode. But since it's not really about writing beautiful code, but rather understanding the concepts, we're just going to make do with this go-to. So what is happening here? So how do we implement the lock operation? Well, we need to test whether currently there's a lock set on the item X that we're trying to lock. So we just test that by checking if log of x is 0. So we can think of log of x as being like a Boolean. And if this test here is true, right? So if the item is unlocked currently, then we just set the log to 1. So that's what this left arrow here means. It's an assignment. Otherwise, we need to wait until this log of x is equals to 0. And then the log manager will wake up the transaction that is waiting. Okay, and otherwise, and afterwards, we just we jump up here to this label B here, and then try again. So it's very simple. And similarly for unlocking, this is even simpler, right? Because I just need to set that Boolean to 0, unlocking the item. And what else needs to happen? Well, if any transactions are waiting, then we're going to wake up one of them, or rather the log manager is going to wake one of the waiting transactions. Now, if you take a closer look at this code here, is there any problem? If I'm executing this in a concurrent environment where multiple transactions, so for example, multiple transactions may try to acquire write lock on item X. Yeah, so I'm assuming by waiting forever, you mean that some transaction may starve. That's true. But there's actually a more crucial problem here. Because these two lines here, this testing of this Boolean, whether it's 0, and the setting of the Boolean to 1, those two don't really happen in one single atomic step, right? Because they're two different statements. So to make this work, you need to use some synchronization mechanism. So you would need to make this these two atomic by, for example, in Java, you can use the synchronized statement. So you put these two into a synchronized block. Because if you don't do that, well, what can happen? Well, you have one transaction, T1, that tries to, let's say, acquire a write lock on X. Okay, so it will execute this code here. So it will, and let's assume that X is currently not locked. So this will return 0. All right, great. So then the transaction will next execute this line. So it will try to set the lock of X to 1. But unfortunately, some other the scheduler will, for some reason, the operating system will pause this transaction. And now some other transaction starts executing, which also wants to acquire a write lock on X. And therefore executes exactly the same code. And well, it's going to read that the Boolean is still 0 because transaction T1 hasn't executed this line yet. So it will also execute this branch of the if condition. And now what happens is that both of them will just set the Boolean to 1. And both of them have acquired a write lock, which is not good, right? Because we want to make sure that the write lock is exclusive. And therefore, we can't we need to make these two statements here atomic, okay? Now, if I don't want to use these synchronization blocks, there are other ways around that. So let's see if that's possible. And that we're going to take a slight detour here by looking at how we can implement locking with simple read-write variables without adding these atomic blocks. Okay, so I don't want to add any synchronization blocks using Java, for instance. So I just want to implement the functionality of, let's say, a write lock by using simple variables. Yeah, I mean, you need to throw an exception. The problem is that neither of these two transactions will know that an exception has happened, right? Because they're both concurrently or executing this code here, so they have no idea what has happened. So that the problem is that when a transaction tests whether this Boolean here is 0, and then there might be a long time before the transaction can actually execute this line of code here. Maybe some other transaction has already executed this in between if there's no atomicity between these two lines. All right, so let's see how we can do this. And for that, we're going to look at this story here. So let's assume we have Alice and Bob. So this is Alice over here, and this is Bob. And they're both computer chips. So they're both kind of, you can think of them as being transactions. So we have one transaction that we call Alice and one transaction that we have Bob. All right. So Alice has a pet, and also Bob has a pet. And these pets like to play in this pond. The only problem is the pets don't get along. So what kind of protocol do we need here to avoid these pets being in the pond at the same time? So to formalize this problem, basically what we want to solve is we want to solve mutual exclusion. So we want to avoid that both pets are in the pond at the same time. So that's the mutual exclusion property. So only a single pet should ever be in the pond at the same time. And we also want to ensure no deadlock. Okay, so if only one pet wants to get in, then it will get in. And if both want to get in, one of them will get in. All right. And I see in the chat, one suggestion is to divide the pets. Yeah, sure, if you could divide the pond between the two, but these pets don't look as if they're very cooperative, so this might cause some problems. So let's come up with a simple protocol. Well, just look at the pond, right? Why it doesn't work is that looking and then doing something is not an atomic operation. In fact, that's exactly what we did in that simple naive implementation of the locking function, right? So we were testing a Boolean and then doing something by writing to that Boolean. So if we don't, if that's not an atomic operation, then this simple protocol to just check whether the other pet is in a pot before you let your own pet go into the pond, that won't work. So the second protocol that we can look at is the so-called cell phone protocol. So how does that work? Well, Bob calls up Alice, or vice versa. Right? Unfortunately, again, we have some problems. What if let's say Alice calls Bob, what if Bob is in the shower, he can't answer the phone? What if one of them needs to recharge their phone battery, or Bob is out shopping for pet food, and so on, right? So the cell phone protocol basically requires both parties to be there and to be monitoring their cell phone. Okay, so the problem is that the recipient might not be listening or available. And to solve this problem, we need to use communication that is persistent, like writing to a variable, and not transient, right? So like speaking. Okay, so whatever you do needs to be observable later on. So let's come up with the second protocol idea, which we call the can protocol, because it's based on using these soda cans here that you can place on the windowsill, and you can tighten some rope around the can, and then if you pull at the rope, you can knock down the can. Okay, so that way we can convey a bit between the two. So let's say we have some can here placed on Alice's windowsill, and this rope here is held by Bob. So Bob can pull this rope and kind of send a signal to Alice. Okay, and even if Alice is not there at this point, because Alice is out, when Alice comes back, she can see that the can has been knocked over, and therefore Bob has given the signal. Okay, so more concretely, we're going to place these cans on Alice's windowsill, and the strings that are attached to these cans lead back to Bob's house. Whenever Bob pulls a string, it will knock over one of these cans. Now, unfortunately, this protocol too has some problems. One problem is that you need to reset these cans each time you use them, because once you have knocked over the can, once you have knocked it down from the windowsill, Bob can't just walk over there and put it back up. That would take too much time. And at some point, Bob may run out of cans if Alice is away. So even if you have multiple cans standing there, for instance, each time Bob wants to release his pet, he could knock over a can. So at some point he would run out of cans if Alice doesn't reset them. Okay, and again, the interpretation is that we can't solve mutual exclusion with so-called interrupts. An interrupt is like the sender setting a fixed bit in the receiver's memory space, and the receiver would need to reset the bit when the receiver is ready. And in fact, you can show that this requires an unbounded number of interrupt bits, and since interrupt bits correspond to cans, we would require an unbounded number of cans. So if you can't exactly follow this interpretation, don't worry about it. So now let's look at a protocol that brings us closer to what we want. And we're going to call this the flag protocol. So Alice has a flag and Bob has a flag, and they can both observe each other's flag. All right, so how does this protocol work? Let's look at Alice's protocol. So Alice is going to raise the flag, and then she's going to wait after raising a flag until Bob's flag is down. Okay, so Bob's flag is currently not up. Then Alice can release her pet, and once the pet returns, she can lower her flag. All right. And what about Bob's protocol? Well, Bob is also going to raise his flag, and then he's going to check whether Alice's flag is down. If Alice's flag is down, he's going to unleash his pet. And finally, he's going to lower his own flag once his pet returns. Okay, so the flag is kind of a signal that I want to release my pet for Bob and for Alice. All right, so here we have Alice's protocol, right? So we're raising the flag, we're waiting until Bob's flag is down, then we unleash the pet into the pond, and then we lower the flag when the pet returns. So it's a very simple protocol, and of course Bob's protocol is exactly symmetric. So I'm just replacing Alice here. So Bob here with Alice in the code. So now the question is, does this work? Are the pets gonna end up in the pond at the same time? Is it possible that they both end up in the pond at the same time? It's not possible, right? What about deadlocks? Can we have a deadlock? Well, we might have a deadlock, right? So let's think about this more carefully. So let's assume both pets want to go in, right? So what's going to happen? Well, Bob is going to execute this code. Alice is going to execute this code. So what are they going to do? Well, Alice is going to raise her flag, right? Then Bob is going to raise his flag, sorry. And he's going to wait until he sees Alice's flag is down. Similarly, Alice is going to wait until she sees that Bob's flag is down. So neither of these two conditions here is ever going to be satisfied because they both raised their flags. All right, so in that case, neither of the two pets is ever going to get into the pond, and we're stuck in the deadlock. All right, so we're not quite there yet, but we can fix this by making Bob's protocol slightly different. Okay, so we're not going to change Alice's protocol. Okay, so there's a question. So they raised their flag initially. Yes, right. So this was the protocol, right? So the first, both of them first raise their flag, then they wait until Bob's flag is down, and Bob waits until Alice's flag is down, and only then they unleash their pet. And this unfortunately leads to a deadlock. So let's change Bob's protocol in the following way. So he still raises his flag initially, and then he checks whether Alice's flag is up. And if that's the case, he's just going to lower his own flag. And then he waits for Alice's flag to go down. Okay. So once Alice's flag is down, once he observes that, then he will raise his own flag, and then he will jump back up here at the start of this while loop, and again check if Alice's flag is up meanwhile. Right? It could have happened that since the last time that Alice's flag went down, it's already back up, and so he needs to check again. Okay, so Bob defers to Alice in case both of them are trying to get in. Although the rest of the code is the same, right? So so once Alice's flag is down, Bob will be able to unleash his own pet and lower the flag when the pet returns. Okay, so this algorithm contains something that is known as the flag principle. So what both Alice and Bob are doing here is to raise the flag, and then they look at each other's flag. Okay, and the reason why this works is that if both of them raise their flag and then look, then the last one who looks must see both flags up. Okay, so let's see why this satisfies mutual exclusion. Well, how can we show that? Well, we assume that both pets are in the pond. We assume that in the contradiction, because of course we don't want that to happen. So let's assume both are in the pond. Let's just derive a contradiction by reasoning backwards. So let's look at the last time that Alice and Bob each looked before letting their respective pets in. And let's assume that Alice was the last one to take a look at Bob's flag. Okay, so this is the scenario that we have. Time is flowing from left to right. So suppose both pets end up in the pond at some point here. And this was the last time that Alice looked and didn't see Bob's flag. Because if she had seen Bob's flag, she wouldn't have let her pet in. All right, so from the protocol, we know that before Alice looked the last time, she must have raised her flag, because that's how we specified the protocol. All right. So when was the last time that Bob must have looked at Alice's flag? In this timeline. Exactly. Before Alice raised her flag. Why? Why can't this point in time here be afterwards, for example, here? Or maybe even here? Well, we already assumed that it's not here because we assumed Alice is the last one who looked. So why can't it be, for instance, here? Because we know that Bob unleashed his pet, right? So at this point, at some point here, those pets are in the pond. Okay, so we know that Bob released his pet. So since Bob looked at Alice's flag in this event here, this event must have happened before Alice raised her flag, because otherwise Bob would have seen Alice's flag, right? And he wouldn't have unleashed his own pet. So that's why we know that this must have happened at some point to the left of this point in time. Okay, so we know that the last time Bob looked was here at some point. All right. Now, when was the last time that Bob raised his own flag? In this timeline. What do we know about that? Well, we know by the code of that algorithm that that's the first thing that Bob does, right? So whenever Bob checks whether Alice's flag is up, he has already raised his own flag. Okay, so therefore, this must be to the left of this event and at some point here. And now we're already done to show that this isn't possible, because since Bob raised his flag here, Alice must have seen Bob's flag, right? When she looked at it. So what I mean by they raised the flag initially is that, so Alice and Bob only execute this code when they want to unleash their pet, okay? So initially, as they execute this code, that's when they raise the flag. Of course, if Bob doesn't want his pet to go into the pond, if then he's not going to raise the flag. His flag is just going to stay down. All right. Okay, so we have a contradiction because Alice was looking at Bob's flag here and she didn't see it. Good, so we know that mutual exclusion holds. So what about deadlock? Well, if only one pet wants in, meaning the other pet doesn't want in, so let's say only Alice's pet wants in, then Bob is never, and Bob's pet does not, so then Bob is not going to raise his flag, and therefore Alice's pet will get in. So that's fine. And you know, to get a deadlock, we would need to require both pets to continually trying to get in without succeeding. Okay, but we know that if Bob sees Alice's flag, he will give her priority, right? Because he's going to just lower his own flag and then try again later on. All right, so again, this shows that deadlock holds. And don't worry about these formal arguments here. They're not going to be part of the final exam. This is just for your understanding. So let's look at some remarks about this. So from this flag protocol, we can implement write locks and read locks by using only simple read-write variables, because that's exactly what such a flag is. It's a variable that you can either set or unset. The downside is that the number of required read-write variables is exactly equals to the number of transactions, right? So if we have more than 2 transactions, we also need more flags. Okay, so if you want to scale this up, then you need one variable for each participating transaction, and that doesn't really scale up if you have a lot of transactions. Another problem about this protocol is that it's unfair in the following sense. So Bob's pet might never get in, because if Alice's pet wants to go into the pond, Bob is always going to defer to Alice. Okay, so the starvation property, the starvation might still happen of this transaction. So how is locking implemented in real systems? So it's not implemented using these simple read-write variables, but instead by using atomic hardware operations such as test and set and compare and swap. Okay, so these kind of operations allow you to test a variable for some value and also immediately in the same atomic step set it to some other value. And then we won't run into this problem that I mentioned earlier on. All right, so in the last few minutes of today's lecture, you're free to ask me any questions, of course, and also if you have a few moments to fill out the teaching and learning questionnaire, that would be great. So there's a question, how about setting a timer? A timer for? Well, I guess the problem is that, you can use timers to implement these things. The problem is that when we do that, this degrades the performance when there's only, let's say, a transaction that doesn't conflict with anyone, right? Because that transaction still will need to use a timer, and only when the timer expires, it will be able to actually, acquire a lock. And if there's no other transaction accessing the same item, we don't want that transaction to wait. So we want to execute it as fast as possible. There's another question whether I can give an example of a cascade list schedule, not this strict schedule. So we're going to look at that in the tutorial. All right, and my office hours at 6 p.m. Just a reminder. Otherwise, I'll see you either in the tutorial or next week in our final lecture.